Okay, so let's start this new topic, tangent lines. Now we know pretty well about tangents to circles, and we see this very early in school itself. Whenever we start learning Euclidean geometry and circles make an appearance, tangents also come soon after. And tangents to circles look like this, of course, which are lines that just touch a circle. Like this one, the line L just touches the circle at the point P, at only one point. And one more thing you can see is that the tangent line, apart from touching the circle at P, does not have anything else to do with the circle. It stays outside the circle. And there is one more observation. If you draw a line segment joining the center of the circle and that point P where L touches the circle, then that is perpendicular to the tangent line. But what does it mean to say that a line L is a tangent to a curve C, so which is not necessarily a circle, at some point P on the curve? We can take our cue from the geometry of the circle and can keep these 3 points in mind while trying to generalize the notion of tangent to general curves. Say we observe from this that the line L passes through P and is perpendicular to a line from P to the center of O. Okay, what we have just now observed. The problem is that for a general curve though, centers do not have any meaning. Okay, centers only have meaning for circles. So this observation falls flat here itself for a general curve. Forget about the line joining that center because there is no obvious center for a general curve. So what about the line segment joining the center to that point being perpendicular to the tangent line? So this first observation becomes useless for general curves simply because of the fact that centers are not well defined for any curve. For circles, of course, centers are there, but for a general curve, there is no such notion of center. There is a second observation though. L passes through only one point P of C, one point of C, namely P. This also, however, becomes problematic when we consider a general curve. Let's see how. It's not very difficult to create problematic examples that will make all these observations pretty useless. For example, you can take this curve. Let's also show the coordinate axis, y-axis and x-axis. Suppose this is our curve C, which is not a circle. Okay, say for example it's a parabolic curve, it's a parabola. You can then think of a line like this, L, which passes through the point P on C. Then the second condition for this line and this curve is true. L passes through only one point of C, and I say that this is a parabolic curve because this curve is not going to come back together. Okay, so if we are drawing the line carefully, this is the only point where the line L is going to cross C, only once, not more than once. Okay, because those parts are going further and further away. But will you call this L a tangent to C at P? Of course not. So that means this condition also becomes useless when we take the notion of tangency to general curves. There is a third condition though. L passes through P and lies on only one side of C. Oh, but by the way, I forgot. Even if you have this type of behavior for L and the curve is a general curve, still L may fail to pass through only one point of C. Let us see that example also. Say your curve is like this, a kind of a wavy curve, something like this. It may happen, and say you consider this line. Okay, so this is your curve C, extending on that side, on this side. Somehow a portion of the curve has been shown, and this is your line L, which actually passes through P and has tangent like behavior, like that kind of behavior. Although we do not have any center here, but forget about those things. Here L is crossing C, but here L is touching C at P. However, only one point, that condition has been violated here. And you can understand that by choosing a curve sufficiently wavy, you can make this line pass through as many points of the curve as you want. Okay, so that unique point, that condition is gone, despite the line L showing that tangent like behavior. So that is why this uniqueness, this cannot be kept as a condition in our tangency when we are talking about tangents to general curves. There is one more thing though. L passes through P and lies on only one side of C. This we see happening for circles because all the tangents lie on the outside. Now for a general curve, of course, you cannot consistently define outside or inside, but you can say, guess that, okay, I will try to keep the tangent line on only one side. Here also there are problematic examples, and let's see one such. Say you think of a curve like this, and you carefully choose a point P here so that a line passes through that point only. Of course, the way I have drawn it, it seems like this line has passed through many points of this curve. But you can imagine that if we magnify this sufficiently, the separation between this line and this curve will become more and more clear, so that actually the line is passing through P only. This is our L and this is C. So in spite of showing that tangent kind of behavior, here L does not lie on one side of the curve, but parts of L lie on this side, parts of L lie on that side. So this lying on one side also becomes a problematic condition. However, incidentally, when we do see what the actual definition of tangents to any curve is, we will see that this is not a tangent to C at P, but this is a tangent to C at P, and this is also actually a tangent to C at P. So what we need is not static conditions like this, but a dynamic approach in which things will change, and we will get the tangent as a kind of a limiting object, the kind of thing that we considered back when we were starting the study of limits. Those examples where we saw the population of flies changing, and also that stone was dropped, if you remember, from a 150 feet cliff, and we were asked to calculate average speeds and then instantaneous speed. So for those situations we drew graphs, and there we went through such processes. We first considered secant lines, and then we gradually made those secant lines tangent by keeping one point P fixed and moving a nearby point Q on the curve towards P. Okay, so the general process, the dynamic process that we are talking about here will involve this. It also has steps. So the first step, the authors write, we start with what we can calculate here. We start with what we can calculate. I don't want to change the language that the authors have chosen, okay, because when you see the actual sentence that they have written in the book, that may have many hidden meanings, okay. We do not want to lose that, so I don't want to write this in my own words. We start with what we can calculate, namely the slope of the secant PQ. Well, of course, then you may ask what is Q? Where Q is a point, on this part I am writing extra just to make it clear, where Q is a point on C near P. P is already on C, but Q is also a point on C which is close to P. And we will make Q closer and closer to P. So what we are saying here is that, say you have the curve in, the curve can be whatever shape. So on the curve you have P somewhere, and very close nearby you have Q again on the curve. So you can join P and Q by a line. That will be your secant line, and then you keep P fixed and bring Q closer and closer to P, while always maintaining that Q be on the curve, of course. Okay, so Q moves towards P while always being along the curve. And then the secant line will also accordingly continuously change. And what we are saying here is that we will calculate the slope of the secant line. So the slope will also change. Now in the limiting position, the slope, when Q approaches P, the slope is changing because the secant line is changing, and that quantity will have, if it has a limit, that limit we will define as the slope of the tangent to the curve at the point P. So instead of straight away defining the tangent at P to see geometrically, we take the help of slope and take the help of limit. Then what we do? What we can calculate, here is an emphasis on can. And then in the second step, investigate the limit of the secant slope. Yeah. Investigate the limit of the secant slope, if it exists. Yeah, it may not exist also. Well, okay, that condition will be included in the investigation itself. As Q approaches P along the curve C. And finally, if the limit exists, take it to be the slope of the curve, the slope of the tangent at P. Okay. If the limit exists, take it to be the slope of the tangent at P and define the tangent to be the line having this slope. Just give me a moment, okay? Having this slope and passing through P. So that will be the process in which we will find tangents to curves at some given point. Now geometrically, if we just simply try to understand the process, say we take a curve like this. Let me just take the curve sufficiently. It's not a part of a circle, okay, although it looks like that, but I am taking it sufficiently curved just to make something clear. Say the point P, where we want to define the tangent to the curve, let's call the curve C also, lies there. Okay, that point P lies there, and now a nearby point is Q on the curve. Now this of course looks like it's somewhat far away from P, but that's only because I want to make the diagram clear. So you join P and Q and you have this secant line. This line has its own slope. Then what you do, you keep bringing Q closer and closer to P, keeping P fixed. And every time you choose a new position for Q, the secant changes. Its slope also changes. So you get many slopes. Say the slope of this secant is, say, S1, okay, and this is S2, this is S3. So you get a sequence of slopes. Actually, I should not use the word sequence, but I'm just simply saying, okay. Now, if this, do not attach too much significance to this n, okay, just simply instead of writing s, which looks like a constant, I am writing Sn. As Q approaches P, it's not something rigorous, I am just using this symbol to indicate the process. If this limit exists, and say this limit has some value s, which is a real number, then we define s to be the slope of the tangent at the point P. In other words, we define the tangent to be that line which has this slope s and it passes through P, and we already know from our study about straight lines that when we are given the slope of a line and a point through which the line passes, that's enough to determine the line completely. And that will be the tangent. By definition, that will be the tangent to the curve at P with that slope and of course passing through P. And keep in mind that this has to be done from both sides. So here we considered Q that lies on that side of P and then brought Q closer and closer to P. However, you should also do this process by taking Q on that side. For that though, I cannot of course change the curve or P, but let me just, for the sake of clarity, extend the curve a little bit on that side also. Now your Q is here. So your secant will look like this. And then you make again Q closer and closer to P. So these new secants will also have some slopes of their own, and that slope also has to, those slopes have to reach the same limit. Okay, then only we say that there is a common limit which is to be taken as the slope of the tangent to the curve C at the point P. And also keep in mind that whenever you are going through this process, you should not encounter vertical lines, because vertical lines do not have any slope, but that of course can be avoided easily by taking things carefully. Now let's see one example and see how actually we can use this process in a concrete situation to find the tangent to an actual curve at a given point. So this is example 1. This is much better because here you get the thing that you want without having to devise such strange geometric conditions, and every time you give a new condition, you see that no, there is an example in which the condition fails and the entire thing becomes useless. So without having those problems, this is this is how tangents are defined, and this is the only way that tangents can be defined. And one more thing is that because there is a possibility of the limit not existing, so you will see that there are situations in which some curves do not have tangents at some points. Maybe not everywhere, but at some points, some curves do not have tangents because this process may not have a limit. That may happen if you are, say, taking Q towards P from one side, say, if one-sided limit fails to exist, or both one-sided limits exist but they are not the same. In that case also, tangent will not exist. And in this example, we are going to see a parabola. Find the slope of the parabola. Okay, there is something else also that needs to be made clear here. Let me first write down the example statement and then I will explain. At the point P 2, 4, write an equation for the tangent to the parabola at this point. You may have noticed one thing here which may not be clear, which may be confusing. Find the slope of the parabola at this point. Slope of the parabola at a point. Now, what type of idea can this be? We only know that straight lines have slopes. How can a curve have a slope at some point? Well, the idea is just then again the slope of the tangent. You see, you have to, you cannot just simply mechanically take this as simply an idea. You have to see geometrically, and you should convince yourself that when you draw a curve, the curve can be any type of curve, it can have any shape. Now, when a curve deviates from being a straight line is also technically a curve which does not deviate at all. It just continues to go in that same direction. However, when you consider a curve like this which deviates from being a straight line at every point, like this one, still at a given point, it has a direction. Just at that point, if you draw the tangent, the direction of the curve at that instant is the direction of the tangent, which you can better appreciate if you think about circular motion of some object. Say you have tied a heavy object to a string and you are pulling it towards you, or at the same time you are rotating. So the heavy object will follow a circular path, that is circular motion. Now, as you increase your pull, the object moves faster and faster. But if at one point the string breaks, you see, at every moment in its motion, the object of course is changing its direction, continuously changing its direction. But if the moment the string breaks, the object will fly apart. In which direction? In the direction of the tangent to the circle at that point. Say the motion is anti-clockwise like this, or what some people would call counterclockwise. Then say at this instant the string breaks, then the object will not fly apart in this fashion or that fashion. It will fly apart along a straight line if no other influence is present. So that means at any instant the direction of the curve, direction of the circle is along the tangent at that point. That is also the case with any general curve, which is why when we say here we are saying no. So this is our parabola and the point 2, 4, if we are drawing the axis like this, say we have 2 here and we have 4 here. The slope of the curve at that point is the slope of the curve's direction at that point. In other words, it is the same as the slope of the tangent at that point. That's what we have been asked to find here. And that of course we cannot do at once. We have to go through that limiting process. Okay, so to solve this, what we will do, this is your point P. So of course the process is just consider a point Q on this side also, on that side. there are actually two processes involved here. And then make Q closer and closer to P, while at every instant you also keep track of the slope of the secant PQ. If that slope reaches a limiting value as Q approaches P either from this side or from that side, then that limiting value will be taken, will be defined, has been defined as the slope of the tangent to the parabola at this point P. That's what we want. But of course, we have the advantage of choosing both sides of Q at once simply by considering this. You see, a point very close to 2, 4 looks like this, 2 plus h, 2 plus h whole square. On which side of 2, 4 it will lie, that will depend on the sign of h. If h is negative, we are talking about this q. If h is positive, we are talking about that q. So you do not have to do it separately twice. You can do it at once. And that's what we are going to do. The solution, consider a point Q on the parabola y equal to x square close to P. Next, what do? You just have to find the slope of the secant PQ. Actually, curves which do not have that natural direction at some given point fail to also have tangents at that point, and as we will see later, fail to be differentiable at that point close to P. The secant PQ has slope delta y divided by delta x. The increment delta y is the difference in y coordinate. The y coordinate of q is 2 plus h whole square minus the y coordinate of p is 4 divided by the increment in the x coordinate. The x coordinate of q is 2 plus h and the x coordinate of p is 2. So this becomes, let me write it here, 4 if you expand this, 4 plus 4h plus h squared minus 4 divided by h. So that gives you this. Now h of course is not equal to 0 because we are not assuming the point q to be the point P itself. No, very close to P but not equal to P, which is why you can cancel h and the slope reduces to this simple form. Now, what will you do to take the limit? Of course, you will make h tend to 0 because when h tends to 0, q tends to P. But because the point q is this, so no matter what h is, this always lies on our y equal to x square parabola. Now, limit as h tends to 0 of the slope of the secant is of course just, this is 4, And that is why, according to our arrangement, 4 should be the slope of the tangent to the parabola at this point. So now we have slope and we have a point through which the tangent should pass. So we can now write its equation. And okay, this is also, but before all those things about tangents, this actually is the slope of the parabola at the point P. And that is why it's also the slope of the tangent at that point. And now your equation of the tangent will become y minus 4 equal to point slope form, slope times x minus 2, because the point is 2 comma 4. So this reduces to what? 4x minus 8, or I am using if and only if, that is double implication, because these are equivalent equations. 4x plus 4 minus 8 gives us minus 4. So that is the equation of the tangent to the parabola at that point. And that's just it for today. So we will see what type of ideas come after this. So that's it. See you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.